Hello everyone, welcome to another webcast of Anybody, which is on simulating physiological performance of assistive devices. So when the topic is assistive devices, you see many studies on the mechanical engineering side, on the joints, motors, mechanisms, and also on the material side. But there are too fewer studies on the impact of that design on the human body. You also see some evaluations that are done experimentally, which is good, but we know that the experiments, they have several limitations because there are some biomechanical variables that cannot be directly measured through experiments. For example, muscle forces or joint reaction forces, they cannot be directly or at least non-invasively be measured. So for that reason, we need like an alternative, which can be computer simulations of biomechanical models, specifically musculoskeletal modeling and simulation. And also these simulations, musculoskeletal modeling and simulations, computer models, have been used a lot in the biomechanics for their analysis. So why not include it in design loop and design pipeline of assistive devices and exoskeletons? So that's the topic that we're going to talk about today. So my name is Mohammad Shourijeh. I'm working at Anybody Technology as an R&D engineer. So I'm going to go through some introduction slides about Anybody modeling system, basically giving you some background that are required to go through the main topic of the presentation, which is on the physiological criteria of exoskeletons or assistive devices. And we're going to have some examples and some results and discussions, and going through some final words and Q&A session. My friend and colleague, Dr. Munki Jang, will be helping with the organization and also the Q&A session. When we talk about musculoskeletal modeling and simulation, the first question that comes into mind is why we need this type of simulations. I think maybe one of the best ways to address this question is to go and jump into the applications directly. So the applications that we've seen in the literature and we're familiar with more or less. So the movement or motion analysis. So just think of a gate lab that you have motion cameras around, you have force plates in the lab, so you can measure some quantities, and later on you can process those data and have access to what's going on inside, for example, to compute joint moments, or access muscle forces. Another application, which is actually the focus of today's webcast, is product design or product design optimization. So let's say you have a conceptual design or you have a prototype, so you have the CAD model for it, but you're not sure about the dimensions, you're not sure about how it's going to affect the human body and physiological aspect of the actual user. So for that reason, you're going to see the interaction between the two parts, which are the design and also the human body. For the ergonomic application, so if someone is coming out or going into the car, it can be the driver or the passenger. So what would be the frame size? What would be, the exterior, the interior of the car to provide some comfort, or to kind of maximize the comfort or minimize the discomfort, or basically providing more ergonomic design. Another application is surgical planning. So you can run comparative studies to see what the outcomes of a possible surgery are. For example, surgery that is done for spine stabilization. So you can do these things as well. And you can export information from musculoskeletal modeling techniques or simulations to finite element analysis to go through more detailed local stress-strain analysis. So Anybody modeling system is the software, is the product of Anybody Technology, and that's the framework that we always talk about. So you have the generic musculoskeletal model that you're gonna adapt it to your specific subject, patient, or population by resizing and basically scaling. That's what anybody does for you. And you can measure also some motions and forces, so external forces and motions through mocap systems, through inertial measurement units, or etc. And you have a device which we call it an environment model. So it's basically something that will be in interaction with the human body, and all these things will come together, and you're going to have a dynamic system. And you can run a musculoskeletal simulation to look at what's going on inside. Namely for muscle forces, tendon forces, ligament forces, energetics like metabolic energy or power, and also joint forces. And you can also close the loop to run something like a design optimization. So feeding back all the information coming from the physiological or biomechanical side to your design, to have a more ergonomic design, to provide more feedback in a good way, in a comfortable way for your users. So when we talk about the environment model and then the device, so the good feature that anybody has, it's that you can have your design, a detailed design, let's say in SolidWorks. So you have designed your CAD model in a very detailed way, and now you want to see the interaction of that design with the human body. So you can export, your assembly file that includes, mates, that includes, the segments, and basically those will be converted into rigid body segments and joints automatically. So using the SolidWorks plugin. And that's very good because the designers like to change their designs and then see the effect in a kind of automatic way. When we have the SolidWorks or any CAD model, and you want to see the dynamic simulation interaction with the human body, we need to talk about a concept called closed kinematic chain, and that's very important. And let's take a look at it. Why it's important. So let's say you have measured the kinematics only. So let's say the human is in interaction with a device, which is a chair in this case. You can see these closed loops. Now we want to talk about why this affects the performance of how you want to use the simulations. So the issue in the closed kinematic chain is that you're going to have infinite number of possibilities and solutions for the kinetic side. So you can have infinite combinations of forces and moments that can, in the same way they can produce the kinematics for you. So we have one specific or one fixed type of kinematics or posture, and then we can use infinite number of combinations for the kinetics. So that's an issue. So someone might ask, okay, then which one is correct? Is the left one correct, or the right one, or all the other possibilities that are infinite that are in between? So from the mathematical and multi-body dynamic point of view, all these solutions are correct. But perhaps when we talk about the biomechanical side, the comfort or ergonomy side, then maybe we lean toward the left one. So, if we assume that left and right hands, for example, and legs are symmetric, maybe it's not a bad assumption to also assume that the loads are carried symmetrically by the subject. But this is a discussion point, and we can talk about it. And there is no specific and fixed answer to this. But what is important is that from our side as modelers, we expect that we use musculoskeletal modeling that gives us the access to these possible and different types of possibilities and solutions. So if you get access to those, you can just change those or pick one of them based on the application. So the closed kinematic chain basically exists in the, even the ergonomic application in sport equipment design. So you see the closed loops between the hands and the arms, and in exoskeletons. So again, why is that important? That's important because in the classical or standard inverse dynamics, people usually use joint coordinates. And what that means is that when you use joint coordinates, you need to essentially open up some joints to still get open chains, because in joint coordinates, only open chains are dealt with. So you need to open up one of the joints to be able to solve the problem kinematically. And also when you go to the kinetic side, so when you want to look at some reaction forces, then you might lead into doing some post-processing. So normally the joint reaction forces are calculated as a post-processing step, which is not very desired for our case, which is the design of assistive devices. So unlike the classical way, the way anybody does it is to use full Cartesian coordinates, which means that any segment has 6 degrees of freedom, and then joints are basically defined based on kinematic constraints. And why is that good? Because it can handle easily the closed kinematic chains, both kinematically and kinetically. And why we need access to the joint reaction forces within simulations, not within the post-processing steps, is that we want to have control on those reaction forces. So imagine that you're designing the device and you want to see how much pressure you're observing at the straps. So your design is good in terms of one of the physiological criteria, let's say metabolic energy or metabolic power, but you also want to see the forces and pressure at different parts of the design that in this case are part of the closed loop. So for that, you want to look at the reaction forces and have them in the loop within the main simulation. So that's why these are very important. So we had 2 or 3 previous webcasts that we talked about different phases of design of assistive devices and exoskeletons. You can have just one phase which is only on studying the motion, and there is no design and device yet. You just want to study, what's going on, how much essentially moment I need, how much force I need. Another step is, the conceptual design, and the last step I would say is the detailed design. So let's say we are at the last step and you have the detailed CAD model in SolidWorks, so you can export it through the plugin that we have, and you're going to have the design in Anybody, the full design actually, and then you can run the simulation to look at some objectives, which are these J, and then you're going to have some constraints and of course some parameters or variables that you're optimizing for. The objective functions can be joint reaction force, activation effort, metabolism, interaction force or pressure, muscle fatigue, the power of your device, is your device is active, and torque. And the constraints can be, the geometry, pressure allowance on the straps, range of motion of the actuators, and kinematic clearance, these things. So this is, when you have the detailed design of your exoskeleton. And you can run design optimization. So now that we have calculated these, we can run and we can have an optimization loop to minimize the objectives, considering the limits and constraints, and find the optimal values for our parameters. But if we are not there yet, so if we are not at the detailed design phase, and we are still, within the conceptual phase, so we can, run the simulation. But as for our device, we can use primitive geometries in Anybody. So we can have, cylinders, spheres, name it. For example, spherical elements and ellipsoidal elements. And for those things, normally those are good enough to have a tentative design, tentative conceptual design in Anybody, and then you can just attach it to your model through kinematic constraints, and you're good to go. So depending on, again, which phase of design you can decide to have more like a fully automatic procedure, which is this one, which is a conceptual design. Or if you're at the detailed design, so you need this part which is outside of the loop. But nevertheless, when you run this part, you can still, feed information back to the detailed design. You're going to see this slide again at the end of the presentation, where we basically go through the ideas that we have discussed and take a look at it again. All right, so when we talk about physiological objectives, people can think of these things very differently. The ones that we'd like to discuss today are mainly the ones that are used in the literature for different problems in biomechanics or used directly for evaluation of exoskeletons. So the first one is metabolic cost. It's been used a lot for evaluation of exoskeletons, and usually through the VO2 masks. So it measures volume of oxygen consumption. Regardless of the cost and the time that you need to put into measuring the data, buying the equipments, buying lab time or renting lab time, basically recruiting subjects and data collection and data processing. Regardless of all these things, one issue that might be in the experimental VO2 consumption is that it only gives you the overall consumption. It doesn't give you the detailed information about individual muscle groups or individual joints. So what if you want to look at one specific muscle group and you want to see, what's causing the overall reduction of the metabolics? Another physiological objective that we're going to consider today is activation effort. So those of you who are familiar with the problem of muscle redundancy biomechanics, you know that in biomechanics, or if you also look at the human body, so we have more muscles than the degrees of freedom in our system. So that means that the system is underdeterminate. And to solve that, we need an extra criterion, and that can be, through optimization. So we normally assume that the human body is minimizing something, which is usually the activation effort, which is normally the sum of cubed activations. And by assuming that, we can solve the muscle redundancy problem. But one question that is still an open question, I think, in the literature is that how we combine individual quantities of muscle activations together to have that overall matrix, which we call an activation effort. And the third and last one will be the joint reaction force. So normally when people for the evaluation of exoskeletons only take into account metabolic cost, that we think only reflects the short-term effects of the device on the human body. However, if you look at the joint reaction force, that will be more like long-term. So the point is, you might be helping the subject with that device from the metabolics perspective, but who knows? If you look at the joint reaction forces, maybe you're overloading the knee joint or one of the joints in your system, which might increase the risk of injury in future. But then when you talk about the joint reaction force, we have multiple joints in our system, so you can have multiple values for the joint reaction forces. How you'd like to combine those is still like the similar question that we had for the activation effort. And when we talk about the joint reaction force, of course, it's the one that includes the contribution of muscles. So it includes, the muscle contributions and, of course, contributions from ground reaction forces. So I'm going to show you a few examples. Two of them are in detail. So this is the box lifting model, and this is the sit-to-stand model. So we're going to talk about, different details of these two models. And this one is an exercise machine. This one is an assistive device for the shoulder, while doing this one is doing sandblasting, and this one is doing polishing. So we're going to go through the examples and discuss a few concepts. So the first example, like I said, is for the box lifting motion, and the device is passive, so it has a rotational stiffness at the hip, and it's supposed to help the hip and the torso. It has two connection or contact locations. One is at the chest, and two are at the right and left thighs. So yeah, essentially it has 3 points of connection. And the idea is basically, when the subject bends over to pick up this, the device will help him to get back up, get basically to the upright position. And the connection between the device and the torso is through a point and surface. So the connection point is basically sliding on the surface, which we assumed was an ellipsoid. As for the motion, we predicted, or we estimated or created that motion within anybody. So we of course assumed some duration and a few assumptions for the type of the motion, like including polynomials for the trajectories versus time. But the key concept is using the center of mass driver, which is a neat feature in anybody. So this blue circle in the middle is showing you the overall center of mass, which takes into account, it's like a collective measure of all the different bodies that are in the system. So all the bones, muscles and elements, the device and the box. So this center of mass is a collective center of mass of all the elements in the model. And then the motion is created in a way that the center of mass, the total center of mass, is in balance. And then the ground reaction forces were also predicted by anybody. The strategy for assistance is like a passive, so it's like through a rotational stiffness or spring. So we have this K that we're going to run a parametric study, and we're looking for optimal value of K. And this theta reference, which is the reference point, will be the upright position. So when the subject gets to the upright position, there is no assistance torque. We changed the stiffness of the device for different values from 0 to 100. Like I mentioned, that was the range that we thought was a broad range to do this study. Here I'm just showing you 4 values. So none means 0, and 25 to 100 means 25 to 100 for the stiffness of the device. So these are not percentage. These are just the stiffness values, so Newton meters or radians. And then the time is normalized time, so it's the normalized time of the box lifting motion. This one is showing you metabolic energy. The next one is showing you the reaction force at the L4, L5. This is just the one that we picked. And the last one is activation effort. So let's look at the metabolic energy rate. So what you see is that when we start from 0 assistance level, and you go to 25 as the stiffness, and then 50, and then 75 and 100, you see that around 50 or 75, that's where your optimal stiffness happens. And then either way that you go away from that optimal point, you're going to increase the physiological objective, which in this case was metabolic energy. You're going to see the same thing when you go to the reaction force, and the same behavior when you go to the activation effort. We grabbed the idea of Pareto front in a multi-criteria optimization, which is basically to have different objectives at the same time, and you can have a plot, a curve, where those objectives are sitting on different axes. And on the main one, you have essentially different values. So each point here is representing one stiffness. And the way we came up with one single value for each objective was that we calculated the mean over time of that objective. And as you see, when we move from 10 to 100, around 60 or 65 is the optimal point that is satisfying and minimizing all the 3 objectives together. If you look at it more closely, you're going to see that 60 is the optimal value for the joint reaction force, whereas 65 is minimizing the activation effort and metabolic cost. So there is a little bit of a discrepancy, and that's actually the point. So you might have different objectives that are not in full agreement with each other. But you know, so 60 was the value that we found was okay and good to optimize the 3 objectives more or less. But let's take a look at it from another perspective. This, I call it like another iteration on the design, or the design with limits. So if you look into literature for maximal skin pressure, you're going to see different values from different sources. So from 20 to 30 to 50, 60, and even 70 or 80 of millimeter of mercury. That's the allowed pressure on the skin. I would say the high side, which is around 70, is the value that is close to basically block the blood circulation. And below that, around 40 or 50, would be sufficient enough to provide enough blood circulation. In this case, we picked 70, which is on the high side, like I mentioned, but our justification is that for this specific motion, the subject is only undergoing the maximal pressure, which is the maximal force, and essentially the maximal assistance level, only at the deepest point of the motion, which is, when the box is almost very close, almost on the ground or very close to the ground. So for that reason, we justify to use 70 millimeter of mercury, which is 9.3 kilopascal. So considering that, we also had an assumption of the size of the attachment area. So we assumed it to be 15 by 15 square centimeters, which makes sense if you just, just try to imagine it on your chest. There's like a box or a rectangle of 15 by 15. That's not very off. So that's given by the design. You could also, run a design optimization on this value as well, of course. But we just assumed that it was given. So considering all these, if we go forward, by looking at the force at the chest, you can calculate a mean pressure, and that would be around 22.5 kilopascal, which is, more than 2 times the allowed pressure. So now we're going to wonder, okay, we ran an optimization kind of problem, and we found that 60 was the optimal. Now we see that we have excessive pressure at the chest. So what we're going to do will be 2 options. One is to send the feedback to the attachment area that we assumed it was 15 by 15. So we might be considering to increase that area, or if not, we have limitation in terms of geometry and the space. The second option is to send feedback to the stiffness. So we assumed it to be 60, but maybe we can find the maximal value that we can have. So the maximum value that we can have to meet that allowed pressure would be around 25 millimeters per radians for the stiffness. And if you go back and look at the Pareto front concept again, you see that although the Pareto front is telling you that around 60 or 65 is the optimal point, but essentially this is your feasible region. So now you have kind of a multi-objective optimization with constraints. So only this part is acceptable. And as we see, this is decreasing, so 25 will be our optimal point. So when we pick this optimal point, we can see how much benefit in percentage we are receiving for using the device. For the metabolic cost, for example, it's around 20%. For joint load, we are showing all the 5 joints that we thought were the most affected ones. So all the lumbar region joints, and also L5 and sacrum. So these ones with circles are the ones that are unassisted case, and the solid ones are the assisted case. So for the joint reaction force, if you look at L4, L5, you're going to see around 25.4% of percentage of benefit. And if you look at the activation effort, you see 62%. So you might observe that the activation effort is far and kind of standing out between the 3 objectives that we're considering. One thing that I need to mention is that for the activation effort, the equation that we used was the sum of activations cubed, sum of cubed activations. which is one of the most commonly used in the literature. The second example is a KAFO device. KAFO stands for knee, ankle, foot orthosis. So the idea is to help the knee and ankle joints. In this example, though, the ankle joint is free to move, so there is no assistance at the ankle, but at the knee, we have a stiffness. So we're trying to help the subject with the sit-to stand. So the subject is starting from this posture and standing up with the help of this assistance, which is the rotational spring at the knee. And the motion is coming from camera-based motion capture this time. So I hope you can see the videos running. Yeah. So I'm not going to bother a lot because the procedure is more or less very similar to the previous example. But again, we ran a parametric study, and the assistance strategy was just rotational spring. So we're looking for the optimal value for the stiffness, but at the knee joint. So the results will show you that for the metabolic energy, around 50 as the stiffness, which is this green one, dark green one, will be our optimal point. And again, if you go further away, either way, decreasing or increasing from 50, you're going to increase the objective, which is the metabolic energy in this case. And you're going to see the same behavior for the two other objectives. The main message here that I need to mention is that so the belief that the more assistance you provide, the better the device is not quite true. So there's an optimal point. Always there's an optimal point that you start to increase the assistance, and at some point it is maximizing or is optimized, and then after that point you're basically decreasing your level of assistance. So it's not that if you feel, okay, I'm going to put more power in the active device, or I'm going to increase the stiffness, it will help the patient or subject better. And again, so like I mentioned, if we look at the Pareto front, 50 is the maximal or the optimal point that we can get for this device. So the stiffness for the knee, for the KAFO device, around 50 will be optimal. And this time, if you remember the previous plot, so in this case, unlike the previous example, this 50 is very consistent between the three objectives. So that's a good point to mention. And when we pick the optimal value, which is 50, we're going to get, we're going to get 26% of benefit for the metabolics, and activation effort around 34%. And this time joint reaction, which was at the knee joint. So instead of L4, L5, which is the previous case, this time we're looking at the knee reaction force only. So it is around 9%. So you might wonder that now this time joint reaction force is standing out and inconsistent with the other two. The third example is an exercise machine. So this device is supposed to have forces at these two actuators. And the CAD model was created in SolidWorks. These blue arrows, these blue lines are the interaction forces at the straps or the connections, which are predicted by anybody. The goal of this device is to provide some antagonistic force on the dorsiflexion side, and essentially plantarflexor muscles are supposed to be more active. So it's an exercise machine for plantarflexor muscles. And the project name was Soleus, which is one of the plantarflexor muscles. Another example is sandblasting. So this guy is holding the device, which is the, holding the equipment, maybe that's a better word. And of course it has some weight, and the worker is doing these type of tasks repeatedly during the day. So it's important to provide some level of assistance with some optimal strategy. So the goal of this device is to have some stiffness, within these joints, and try to help the worker with the gravity forces coming from the arms, and also the equipment, the sandblasting equipment, and also helping the stiffness in the way that the worker needs to push the sandblasting equipment. So you can have multiple strategies in that regard, and you can also run design optimizations for different parameters in your system, which can be stiffnesses and dampings. And the last example is the device that is supposed to help with the polishing task. So again, the workers do these things a lot during the day, and when it goes through years, they're going to go into some injuries. So we want to help the shoulder, which is the most affected joint for the workers. So this device is more or less the same as the previous one that I showed you, but the strategy of assistance is of course different, because the motion is different, and the motion is planar, and the forces at the hands will be different, so the kinetics at the shoulder and the range of motion will be different. So you need a different strategy in terms of stiffness if it's a passive device for these three joints here. So let's go through a little bit of discussion, especially for the first two examples that I showed. So if you remember, we talked about three objectives, and what we saw was that for the two examples, there was a little bit of inconsistency between the amount of benefit that we were observing for different objectives. So that goes back to the concept that maybe we need to consider different objectives together. So thinking of different objectives at the same time. Normally, people only consider metabolic cost for evaluation of exoskeletons. But the question is, so let's say the metabolic cost is okay, so you're actually helping the subject, but you are overloading one of the joints in your system. So you might be helping the guy for short term, but in long term or medium term, you essentially will be causing some risk of injury. So these are the things that we need to consider and discuss in the community. And what we think is the best is to consider, like I said, the objectives together, along with the limits, of course. Another point of discussion is how we collectively add the individual values together. So like I said, the activation effort is common in the literature, that people use the exponent of 3 or 2. But that's still an open question, which one is the best, if we can have weights here, for example, before the activations. And then for the joint reaction force, it's also, I haven't seen much of many studies that are addressing how you can collectively add up the values of different joints together to come up with like an ergonomic score, or come up with a measure that is representative of the whole body performance. Another point of discussion is that we can also think of other criteria. Of course, we only talked about 3, but definitely you can have more. So the strap forces at different parts and locations of the body are very important. The adaptations for the motion and muscular coordination is very important. Fatigue, tolerability, sweating, so that might go also to the material side, is very important. Range of motion, so if the device is limiting your range of motion, although it's helping you with the metabolics or lifting a box, you might not want to wear it comfortably. And the overall happiness is also very important. So some of these can be quantified, and some might go to other fields, like even psychology. So let's take another look at the design framework that we talked about. So again, if we are at the final stage, which is the detailed design, You're going to export your CAD model, and you're going to have your full design, and you can run a design optimization to optimize the parameters that you're after, that are, torques, powers, actuation force, range of motion, for example, stiffness, etc., etc. And the goal is to have all these things, in one go. So you have different objectives that you're minimizing at the same time. Simultaneously, you're looking at and considering the limits and constraints on your problem, and minimizing or optimizing the parameters of interest. So it's very important to have like a automatic procedure. And if you're at the conceptual phase, you're going to have, I'll call it like a fully automatic procedure, that you don't even need this input from the CAD model. You can have primitive geometries in Anybody, and you can run the simulations and close the loop for design optimization. And you can always send feedback to the detailed design for a more detailed specifics to your design. I'd like to thank the funding agencies. So the examples that I showed in this webinar were mainly from the 2 European Horizon 2020 projects called MoveAid and Andy. So these are the URLs to their websites. You can go and check out their websites. So a few wrapping up points. You can check our YouTube channel for previous webcasts. So like I said, there were 3 previous webcasts on exoskeletons. If you're interested, you can just go and find them through our YouTube channel, which is Anybody Technology. You can also go to our website. So this is actually our new website, which was released, I think, just a few months ago. And when you go there, so you can see the detailed publications that you can filter, actually. So you can search for one specific area of publication if you're interested. And you can see different events and dates. And in our website, you can look for AnyScript, or you can actually go directly to anyscript.org, which is the language of Anybody scripting. And you can find useful links how to do and learn Anybody, how to improve your models, and you can see cool videos and examples. And there are future events. So actually, both in June, these 2 ones, the conferences in Germany. So if you're going to be there, please send us an email and we can meet. And the next webcast will be on calculation of the lumbar spine joint reaction forces using Anybody modeling system. So if you're interested, sign up. Thanks very much, everyone. Yeah, one thing that I need to mention. So these are, so we recently created a Facebook page and a Twitter account, and we had this LinkedIn account already. So go and follow us, which one you feel more comfortable with. We actually post, cooler stuff on our Facebook page. And time for questions, so I'll be happy to answer some questions. Just give me 1 minute, and then we collect the questions, and then we come back. Okay, so let's go with the first question. Can anybody scale human model both in general and in subject specific in order to test different dimensions of exoskeleton at the early stage of design? Yes, so the answer is yes, definitely yes. So you can scale the generic musculoskeletal model, to match the anthropometric data, height and weight, and if you have a specific anthropometric measurement of, for example, width of the knee joint, you can also, include and import that information into Anybody, and Anybody will take care of that. And also you can have, medical imaging information to even match the subject specificity even more, so you can match the morphology of the bones. And for the exoskeleton, itself, depending on if you have set the dimensions of the exoskeleton beforehand or not, so depending on which phase of the design you're at. So if you're at the conceptual design phase, so you can have primitives in Anybody which you can parameterize, so you can optimize and scale that design inside anybody, along with other stuff like the scaling of the bones. But if you're at the detailed design phase, so your design will basically be in SolidWorks, so you need to export it into anybody. But once that in anybody, the dimensions are fixed. So if you want to change them, you need to go back. But you can always match the bones and the musculoskeletal model to your design. I hope I answered your question. Okay, so let's go to the next question. Do you need a CAD model in any case? Is it also possible to apply measured exoskeleton parameters, maybe force, movement, assistance, etc., and derive the influence of it by simulation? So I think, we don't necessarily need a CAD model. So depending on, like I said, which phase of the design you're at. So you can have, let's say, before even designing a device, you just want to study the movement that you're interested in. So if you're dealing with gait, for example, box lifting. So if you want to just, study to get a feeling of the amount of torque, the amount of, forces that you need. So, in that phase, you don't need a CAD model. You don't have even a conceptual model yet. But after that phase, you're going to go into the conceptual phase. And what we recommend is that during the conceptual phase, you can have primitive geometries in anybody, like cylinders, spheres, ellipsoids, and that will be enough for having a tentative conceptual design and how to attach it, to the musculoskeletal model, and then you can have a closer look at the forces and the moments. And then the last step will be the detailed design. So once you have done the first two steps, now you have enough information to go to the detailed design. So you go to SolidWorks, for example, you design the details basically, and then you can evaluate it in anybody. And if there is still something to correct and improve, you can feed back the information into SolidWorks. So the next question is, what kind of motion capture data format can anybody import? So yeah, the question is only C3D files? No, so C3D is very, I would say, standard in the biomechanics community, and of course, anybody can import that and use that information for running simulations. Another type that we can use is BVH. BVH is normally exported from IMU-based systems. So, for example, Xsense can export BVH, which is based on joint angles, and that, of course, we can use as well. Also, we can have some types of motion prediction. So, like the example of box lifting that I showed. So, you can have center of mass driver. So, without any previous motion capture data, you can run the simulations and you can predict the motion. By just looking at the balance and when you're driving the center of mass. And also you can have devices. So if you're dealing with sports equipments like the elliptical machine that I showed, you're going to have a lot of constraints from the device. And by the constraints, I mean the kinematic constraints. So those kinematic constraints will impose some kinematics to the model. So most of the motion and posture and kinematics will be given from the imposed kinematic constraints of the device and machine. So let's go to another question. What's the principle of the prediction of the interaction forces between human and exoskeleton? How can anybody handle a kind of statically indeterminate problem if there are more multiple interaction points than the degrees of freedom in the system? So that's a good question, I guess. For that, I think we need to go back to the muscle redundancy problem. So, that's just an example. The muscle redundancy problem, we have more muscles in our body than the degrees of freedom. So how would you solve that? The way it's usually solved is through optimization. So you try to minimize, the effort that is coming from all the muscles that can be, by calculation of forces and sum over them, or the activation, or also metabolic energy is also used for solving the muscle redundancy problem. Nevertheless, so when you're dealing with the interaction forces, that's more or less the same problem. So if you have multiple interaction and actuators or contact elements, so the way you want to solve them is, essentially meeting the equilibrium equations, but at the same time minimizing a criteria. And that criteria can simply be, something that we use in the muscle redundancy problem. So you can essentially minimize the amount of, force, or, depending on how you define the actuators, basically the actuator effort, you can, that's something that you can minimize. And that's true. So that problem is, indeterminate. So you need to solve an optimization. Next question, is there any reference or validation for the prediction of these interaction forces? For instance, can anybody predict the ground reaction force as well? So yeah, exactly. So, actually the main validations that we have is for the ground reaction forces. So there are multiple papers on that. And, maybe we can send the links when we send you the link for the recorded webinar. But we will send you privately for sure the papers. So there are multiple papers, like I mentioned, in Journal of Biomechanics, Multiple Body System Dynamics journals. And there they have basically validated and looked at the prediction of ground reaction forces by anybody versus the experimental reaction forces from force plates. And they've seen a high level of correlation and agreement between the two in different types of movements, like walking, and different types of activity livings and sports. So check for those papers. And maybe we take, another question. Can we define any kind of force or torque controller for actuator modeling inside the antibody inverse dynamics frameworks? For instance, position and velocity-based force torque profiles. So yeah, and I would call, that would be something like a PD controller. So you can have that type of controller in anybody. So you can have, an actuation force or torque, which is a function of, joint angle and joint angular velocity. So what I showed you was just, the torque, although it was a passive system, but the assistive strategy was a function of the joint angle. But you can have, active actuators that are functions of, joint angle and joint angular velocity, or any translational position and velocity, of course. Okay, I think we wrap up and we end the session. Thanks very much, everyone, for joining the webcast. Like I said, we recorded the webcast and we're going to send you the link of the recording. We tried to answer all the questions, but I think there were a couple of them that were remained unanswered. We're going to get back to you and follow up with the questions that were asked and answered, and also the questions that were not. And we're sorry that we couldn't answer all the questions again. So thanks very much again, and have a great day.